Hi, we are from Group 5 Becky. Today we are going to present to you the IR spectroscopy of glucose compound. Let's check it out. Hi, I am Shahira and I am going to explain about the introduction. We were given this assignment to interpret the IR spectrum of glucose compound. At first, we were going to analyze the IR spectrum of Fischer projection of D-glucose. Fischer projection forms two types of glucose structure which are L and D-glucose. L and D-glucose differ in the configuration at each chiral carbon. During rotation by D-glucose, Lex plane is rotated to the right whereas L-glucose is rotated to the left. Glucose also presents in cyclic structure represented by Howard projection. While choosing the IR spectrum of D-glucose, most of the spectrum did not include C-double bond O bone compared to the spectrum of cyclic glucose which shows we have decided to interpret and analyze the IR spectrum of cyclic glucose. This study aims to analyze the structure and vibrational spectra of glucose, a biological molecule that occurs. With a simple three-dimensional perspective, a Howard projection describes the cyclic structure of monosaccharides.
Hi, I'm RAIHAN. So for the body weight assignment, I will explain in detail what this assignment is for. In the IR spectrum, we measure where molecules absorb photons of the IR spectrum. The peaks will represent areas where the specific bonds will vibrate. From the graph, we can see that there are two regions which are simple stretching vibrations from wavelength 1600 to 3500 cm-1 and figure per region from wavelength 600 to 1400 cm-1. The IR frequencies correspond with those of molecular vibration. Molecules vibrate at different frequencies and each vibration involves a specific group of atoms and movements such as stretching, bending, and wobbling. For your information, specific peaks for specific functional group only. Other than that, functional group may undergo two vibrational modes which produce peaks more than one region. From the figure, we can conclude that there is an OH bond at simple stretching vibrations region which shows that the peak is broader than others. Next, because we observe the OH bond, we need to look whether there is a presence of CO bond or not at fingerprint region. So in this figure, the CO bond is present and we can state that there is alcohol in the cyclic glucose structure. Because if the CO bond is absent, we state that the OH at simple stretching vibration is water. Furthermore, if we look more, there are three additional peaks of alkane which CH bond existent just below 3000 cm-1, but CH bond is weaker because the CH bond is stretching a bit little and there is a lack of CH bond at the cyclic glucose structure. The C-double bond O is absent in this figure because we are choosing the cyclic glucose due to its stability, structure, and there is no C-double bond O bond in this cyclic structure. Therefore, we can conclude that there are two functional groups showing up which are alcohol and alkane in this cyclic glucose structure. So I pass to HUWAIDA to explain more about the interpret of the IR spectrum.
There is a broad, strong and weak OH stretching enveloped in figure 3 with two peaks at 3392 and 3193. It means there are two chemically distinct alcohol groups in the molecule with different bond strength, force constant, and hence peak position. Four of the carbons in the glucose ring are structurally similar, each being attached to two other carbons, one oxygen and one hydrogen, with the oxygen each being part of the secondary alcohol. We will call the situation where there is only one hydrogen attached to a carbon, a lone hydrogen. The lone hydrogen in glucose are all saturated and hence will have CH stretches below 3000. However, this peak will not be as intense as typical CH stretches since there is only one bond contributing to the peak intensity instead of 2 or 3 as is in the case for methylene and methyl group. Saturated lone CH group tend to have their stretching peaks around 2900. The oddball's fifth carbon in the glucose ring has a primary alcohol group hanging off it that contains CH2 groups. It is the CH and CH2 meiosis that are responsible for the small CH stretching peak shown in figure 2 around 2900.
Hello everyone, I am IZZATI and I will go detail on how to interpret the glucose spectrum. As we read the spectrum from left to right, the first peak we encounter is about 3392 cm minus 1 peak. From the correlation chart, this wavelength fall in the range of 3550 to 3200 cm minus 1. This range indicates strong and stretching OH bond. The next obvious peak that can be seen is 3193 cm minus 1. In the correlation chart, this peak belong in the range of 3200 to 2700 cm minus 1. So it is easy for us to assume the weak OH bond in our spectrum. For the next peak, 2944, 2913 and 2891 cm minus 1, our assumption is correct that this wavelength is the same compound class alkene, cause all the three wavelengths fall in the range of 3000 to 2840 cm minus 1 and stretching. The absence of C double bond O peak confirm the cyclic structure of our glucose. The next interpretation is in the fingerprint region where the peak is 1457 cm minus 1. This wavelength shows the bending of CH bond in our glucose when we compare to 1465 and 1450 cm minus 1 wavelength. Then we proceed with the next peak, which is 1224 to 1048 cm minus 1 peak. As we are already aware of our compound structure, we reject unrelated bond and choose that all these wavelength represent C single bond O. All these bonds appear as a strong and stretching bond. Recall back in our class, CC bond cannot be detected in IR spectrum as their movement is very weak. However, the CC bond is still present. All the peaks were compared from a table provided by Sigma Aldrich. This is the end of our interpretation because our syllabus doesn't include further interpretation in fingerprint region. Note that some peaks cannot be identified as they appear by a noisy movement of various bonds. That's all from glucose spectrum interpretation. Thank you.
Hello, I'm HASYA. I will present on how we know the compound is glucose and how we know that is in the ring structure. After we finish interpreting compound, we can conclude that the shape produced from each functional group in the compound is different, where the weights vibrate either stretching, bending and wobbling is produced at different reagent and wavelength according to the different bond of different element. After interpreting the compound, we found that it is a glucose because of the presence of peak at 3193 and 3392 show that the analyzed compound has hydroxyl group which is OH. In addition, there is also a peak produced at 1105 up to 1372 which indicates the existence of C bond O. The resulting CO bond peak proved that the OH bond is not from the water but from the hydroxyl group. Glucose can exist in the form of a ring structure or open chain structure. Glucose changes its structure from open chain to a ring structure spontaneously where the aldehyde group react with the hydroxyl group to form a hemiacetal and keto group react with hydroxyl group to form hemiketal. Since there is no existence of C double bond O at 1710 indicates that there is no carbonyl group which structure glucose in the form of ring structure. That's all assignment that has given to us from 5 Spectroscopy. Thank you and have a nice day.